Okay, so let's move on to our last example, our practice for neural networks. And basically, we're going to be working with a file called concrete.csv. What this file contains are basically, for each row, we have information about, different concrete samples that have been collected. And for each concrete sample, we will have the strength of that concrete sample, and we will also have a specific metrics for a set of characteristics characterizing that piece of concrete with, for example, variables like amount of water, amount of cement, and so on. And so the idea here is whether we can predict the strength of the concrete based on these different features, right? Okay, and we're going to try to predict that using neural networks with different numbers of neurons and with different numbers of layers.
So neural networks typically work better when input values are small values. Okay, so you don't want your input signals to vary widely numerically. So what's a good practice to do? It's typically to normalize all the features. Okay, and once all the features are normalized, we can go ahead and train the model. So what I'm going to be doing now, it's basically loading the CSV file, the concrete CSV file, and then I'm going to be creating a normalization function, which is the one that you see there, the normalize. Okay, and what the normalization function is doing is basically it's taking a given value x and it's normalizing it. And the type of normalization that we are applying is just simply by subtracting the minimum value across all the values and dividing it by the difference between the maximum and the minimum value. Okay. So we are applying that normalization for the entire data frame, which means that we are taking the minimum and the maximum values, and we are using those as our normalization factor. So the second step, the apply normalization to the entire data frame, you see there the only thing that some of you might not be able to understand is the lapply. Okay, what lapply does is that it basically applies a function to an entire data frame. So what we are saying is, okay, given the concrete data frame that we have just read, apply the normalization function to all of the values in there. Okay, and so as a result, what we will have, the concrete norm, which is the concrete data frame normalized, it's exactly the same data frame, but the values are normalized, right? So what we want to check is that the distribution of values, which are now going to be between 0 and 1, but at least that the distribution of values, medians, the value for each quantile and so on, is similar to the original distribution. Okay, so let's go ahead and try this. So the first thing that we need to do is read the CSV file. Okay, now I'm going to define the normalization function. So I create a function. That's not correct. I create a function, and every time it's going to return a value x minus min x divided by max of x minus min of x. That's this one and that's this one. It should be correct. It's always good to check that the parentheses are fine, right? So what we do is that we create now a normalization data frame, and we make sure that this is saved as a data frame, okay? And we apply to the concrete data set the normalization function. Okay, so now all the values in the normalization data frame are between 0 and 1, but we want to let's take a look at the summary. So if you take a look at the summary of concrete norm at the strength values, okay, this is the distribution. If you take a look at the distribution of the strength, is this one, okay? So as you can see there, the distributions, the values that you see there are different because obviously we normalized between 0 and 1. So compared to the original minimum and maximum, you see we started with a 2.33 and a maximum of 82. We now are between 0 and 1. But the distribution of the values is respected. Okay, so now we can in fact create our training and testing dataset. Remember that we want to use neural networks to predict the strength of the concrete based on a set of features. So we create concrete train, taking the the concrete normalized. We take the first 773 and then we create a concrete test that contains the remaining samples. Okay, perfect. So now that we've done that, let's use, we're going to use a library called Neural Net. And basically what I put there is a PDF file where you can check more details about the package as usual. I mean, I'm just giving you a few examples of how each package is used to basically train and test on a data set, but all the functions that I keep explaining, you know, throughout the classes in this course have many options. It would be impossible to explain all the options, but in R, every command, every function that I explain, it has a PFD file explaining, you know, all the possibilities and all the possible features that you can use. So I highly recommend that for your projects, okay, do check and make sure that you understand what every single feature in that package means. Okay, so next thing, let's build a model. Okay, so what we're going to do is we're going to use neural networks to basically predict strength based on all the features that characterize concrete. And the features are written there. So it's cement, slag, ash, water, superplastic, coarse AGG, fine AGG, and age. All these features are the ones that we're going to be using to predict the strength of the concrete. And because we are training the model, so we are using the training data. So let's start with this neural net. We are going to predict the strength, okay, using cement, slag, ash, water, superplastic. Those are not features that I'm making up. Those are the features that, you know, are part, as we saw before, are part of the training data. Coarse AGG, fine AGG, and H. And the data that we use is basically the concrete train. And basically, once we have predicted that, you can actually plot the neural network. So you can, you know, use plot concrete model. And if we take a look, basically this is showing us a super simple model that we have created, okay, which has just one hidden layer. These are all the different input features that we have, and these are the weights that the neural network has computed. Okay. Okay, so, but in the end, what we want to do, the reason why we build this neural network is basically to try and see how well we can predict the strength of concrete. Okay, so what we're going to do is basically predict the strength. And to do that, what we're going to do is use the command compute. Okay, so with the command compute, we are saying instead of predict, okay, so in this case, the name of the prediction function is compute. And what we are doing is say give me or compute me, you know, the prediction using the concrete model that we have just trained, the neural network that we have just trained. And basically what we want to do is use the test data set, but only with the 8 first columns, because the 9th column is the strength that we want to predict. Okay, so the testing data set that we are using is a testing set that we have to specify the features that are going to be used. Okay, good. And after we run the compute function, we basically can look into the final results through different variables within the data structure of the output. I'm going to ask you to look into one of those components, which is called net result. And net result basically outputs all the predicted values for all the different data samples in our testing data set. Okay. There are other variables that you can check, like information about the neurons and so on, but we are going to be focusing on the net result, mainly because we want to understand what's the accuracy of the neural network, and to do that we need to compare the actual output of the network with the ground truth data. Okay, and so, you know, we can look into the model results, and specifically into the net result component, and what you can see here is that this net result what it outputs is basically for all of the points in our testing data set, which are, from 774 onwards, we basically have what's the output of the neuron. Okay, that's a predicted value, the output of the final layer, of the end layer, and that's a predicted value for the strength of the concrete. Okay, and now we'll compare those against the actual values and see how well we are doing. And what we're going to do in this case, because we are predicting a strength, which is a numeric value, it's not a category, right? So we are not going to use a confusion matrix, we're going to use the correlation between the predicted values and the actual values. So net result contains the predicted values. So we're going to take those values and then we're going to compute the correlation between those and the actual strength in the testing data. Okay? So let's do that. So we are going to create a variable called predicted strength, and basically we are taking from model results, we are taking the net result, okay? And those are the predicted values for our testing data set. And then we compute the correlation between the predicted strength and the real strength in the concrete test data set. And the correlation is an 80%, not bad, right? Not bad for such a simple neuron. Okay, it's just like a neuron with one hidden layer. I mean, it's nothing, right? So what I'm going to ask you to do, just try this at home. Okay, this what I'm suggesting here is to basically create another neural network that is going to have 5 different hidden layers. So everything else is exactly the same. So we're using the neural net command to create a neural network that's going to predict strength. The dependent variable is the strength, using the same features that we have used on the training data, but we're going to train it with 5 hidden layers. You can also plot the models. You will see that it takes a little bit more than just with one layer. Okay, it's going to take more because obviously, again, remember that this is the back and forth process of adjusting weights until we minimize the error. But once the training has finished, you can use the compute function to compute the strength or predict the strength on the testing set. And then you can compute the correlation between the predicted strength and the actual strength. You will see that the results are better, okay? The accuracy, the correlation is definitely going to be higher than 0.8. The reason being that by adding 5 different layers, we are adding more complexity to the model, but we also have the ability to model more complex relationships between the different features and the strength of the concrete. Okay. And other things that you can do with the neural net package, as I was saying before, I have shared with you a link to the PDF file, so make sure that you check it and you play around with adding different layers, defining different basically a different number of nodes per layer is also something that you can do. So make sure that you train and test with different models and see whether that impacts the final accuracy. Remember that I'm expecting these type of things in your milestone.